Hello, welcome everyone to this photonics webinar on photonic integrated circuits for next generation OCT. My name is Stijn Kuijvers. I'm a technical sales and project manager at LIGENTEC, and I'm today co-hosting this webinar with Jeroen Biesterbos. Jeroen, welcome. Do you like to introduce yourself?
Yes, sure. So I'm Jeroen. I'm the CCO of SuperLight Photonics, and I'm very happy to talk today about our technology. So thanks for the invitation.
Thank you for joining. So I will kick off this webinar by giving a short overview of LIGENTEC's general capabilities for OCT and other applications. And then we will dive a bit deeper into the technology of SuperLight Photonics. And at the end, I will also give an overview of some of the novel building blocks that we are developing at LIGENTEC to support the OCT community. So let's get started. I imagine most people are already familiar with LIGENTEC, but in case you are not, we are an industrial PIC company in Europe, and we develop and fabricate low-loss integrated photonic circuits. So today we are a team of about 80 photonics enthusiasts, and we have presence in 3 countries. So we have our headquarters in Lausanne, in Switzerland, and we also have offices in Corbeil in France, as well as in Ghent in Belgium. So as I said, we fabricate photonic integrated circuits, and for this we have a strategic partnership with X-FAB, where we do both prototyping but also pilot line production and volume production. And you can see here a picture of our office in Corbeil in France, as I mentioned on a previous slide, right next to the facility of X-FAB. Today we have a unified portfolio of integrated photonic solutions. So we are known for low-loss silicon nitride PICs, but we are also offering now the XPH90 silicon photonics platform, and we complement these PIC solutions with active devices. So we do heterogeneous integration of modulators as well as III-V devices such as photodetectors and other components. So which applications can we serve with our PIC technology? So generally we categorize our applications in 3 different pillars. So the first pillar is mainly on sensing. So this includes OCT, which we will where we will focus on today, but also includes LiDAR, optical clocks, biosensing, fiber sensing, and so on. The second pillar is more around connectivity. So this includes telecom and datacom, but also optical circuit switching and quantum key distribution, for example. And then the last pillar is around computing, which includes quantum computing as well as neuromorphic and optical computing. So in the remainder of this presentation, most of the information that I will highlight will be relevant for OCT. So where are we as LIGENTEC positioned in the value chain? So our core expertise is around the chip manufacturing. As I said, we do both initial prototyping, process development, but also pilot production and volume production. But we also have engineering teams that support our customers on the design side, so designing components and layouting the photonic circuits, essentially translating the product requirements to a PIC, as well as with testing and measurements. So we also have chip and wafer level testing capabilities to support our customers to qualify and test the PICs before they go into their products. If we look at our silicon nitride platform today, we have a number of established standard platforms. So we have based on different silicon nitride thicknesses. So if we look at OCT applications, for example, in C-band or O-band, we often work with our AN350 platform, which is based on a 350 nanometer silicon nitride layer. If we look at OCT applications at shorter wavelengths, for example, 850, we often work with our AN150 platform. And for each of these platforms, we have so-called optional process modules. So these can include heaters, for example, for thermo-optic phase shifting. These can also include rip waveguides to allow polarization management, or our local cladding opening, which can be used for sensing applications. So it's a modular way of working. And for each of the platforms, we also have an extensive PDK to allow straightforward designing and layouting on our platform. Of course, we also have automated wafer testing in line to make sure that the chips that we deliver to our customers are meeting the specifications and requirements. So if we look at some of these platforms that we offer, for example, our AN350 platform for O-band and C-band. We commonly use this platform for its low propagation losses. So this is very relevant, for example, for interferometric circuits in OCT or for delay lines. And we achieve here, this is now for C-band, we achieve single mode propagation losses around 4 dB per meter with very good wafer to wafer and within wafer reproducibility. So you can see that these numbers are quite consistent across the wafer, but also here at the bottom you see the box plots for different wafer runs. If we make that waveguide a bit wider, we can push down those propagation losses further, reaching close to 0.2 dB per meter for a 3.5 micron wide waveguide. So this platform is commonly used by several of our OCT customers, but is also something that we explore in some European initiatives around OCT, such as the PhotonMet project. One other commonly used platform is our AN800 platform, where we use an 800 nanometer thick silicon nitride layer, and this is very often selected when we want to exploit the nonlinear properties of the silicon nitride. So the advantage here is that we have a high optical confinement while retaining the low propagation losses. We also have high power handling, and important is that we can access both the normal and the anomalous dispersion regime, which is important for a lot of nonlinear processes, including supercontinuum generation. And so this technology is also at the core of the technology of SuperLight Photonics. So I will hand over now to Jeroen to dive a bit deeper into their products and capabilities.
Yes, thank you, Stijn. So I just made a slide to give a short introduction of the company. So SuperLight Photonics is a spin-out of the Twente University. We were founded late 22. We're still based in Enschede, the Netherlands. And what we do is we make PIC-based wideband lasers. So we call this wideband lasers, whereas also a traditional name would be supercontinuum lasers. However, we see that our lasers are different in that sense. So we would like to differentiate also from the naming perspective. I will get to that later when we compare our laser also with the classic supercontinuum lasers. So, but let's first talk about how we create this broadband spectrum. We use the curve effect, so short, monochrome, high energy pulses. They self-modulate into a broader spectrum as they propagate through a waveguide. This can be done in two regimes, either normal or anomalous dispersion. And sometimes you also call it positive or negative dispersion. But it's key to say that it can be either normal or anomalous. Both of them, they work until a certain moment when you get to kind of the maximum propagation length in the waveguide. So ultimately, both of them will hit a stagnation point, as of which no further spectral broadening takes place. At that point, you can overcome it by increasing the power. However, this scales very inefficiently with the power. So this is the path that most of the competitors are taking. But ultimately, it results in a very big and bulky lasers, and we'll address some of the downsides later on in this presentation. What we do is slightly different. So we work on the dispersion characteristics, and on the next slide, I will tell a little bit more about that. So how do we improve the dispersion? We use PAD, and I'm going to share a bit of details on that one. Where legacy suppliers use uniform dispersion, so it's either uniform anomalous or uniform normal dispersion, we actually sequence between the two. And that's what we call patterned alternating dispersion. It's good to say that the normal and anomalous dispersion work in opposite directions. So what we do is once we hit stagnation in one regime, we use the other regime to fully compensate. And by doing this multiple times, we can ultimately increase the working length of the spectral broadening process. And as such, we have a much more efficient way to generate this broadband spectrum, which results in substantially lower input power or superior spectral quality, so range, smoothness, The picture on the right shows a typical waveguide where you see these alternating dispersion zones, and on the bottom right graph you see an image how conceptually PAT works by alternating between anomalous and normal dispersion. All right, next slide. So because we have a very straightforward design, we use a chip, we use low power. As a result, also our laser can be relatively straightforward. Obviously, we work in the LIGENTEC AN800 platform. That's where our PAT waveguides are being built. Once we have the chips, we have a third party that makes a module out of them. So we do the chip to fiber welding over there, and then the chips come back to our facility, where we merge them with amplifiers and seed lasers, and that's how we ultimately built a laser. Then next slide. Just a brief highlight of the markets and applications that we cover. So scientific, industrial, and medical markets are being served. The prime market is OCT, and that's also where we're going to talk about more today. Besides that, we also do regular spectroscopy, spectral imaging, and these kind of applications. So maybe a first word on OCT itself. So this is an indirect way to sense spectroscopy, so not direct spectroscopic measurements. So you compare a light that went through a sample with the original light. So this is creating an interferometric picture. So the light splits into a sample path and a reference path. The light recombines after it passes through the sample. This interferometric pattern is being analyzed, and we apply a Fourier transform on that one to ultimately get to a one-dimensional intensity versus depth graph, which is called an ASE scan. And then you can do multiple ASE scans. You can stitch them together, either in a 2D cross-section, which is called a B scan, or you can add another axis, and then it becomes a full 3D image, also called a C scan. There are two ways to do OCT, spectral domain and swept source OCT. In the first instance, you use broadband light in combination with a spectrometer. And this is, of course, where we come in. We compare different light sources, incoherent light, and SLED, the legacy supercontinuum lasers, and our own wideband lasers. The older technology uses tunable lasers in combination with a photodetector. But for today, we're going to zoom in a little bit more on the broadband light sources that support spectral domain. So, SuperLight, we have a unique combination of brightness, spectral range, stability, form factor, and scalability. So if we compare this to the three other technologies that were mentioned on the previous slide, we look at incoherent sources. They are very limited in brightness and limited in lifetime. So here you see that in terms of spectral stability, spectral range, they perform quite well. But just the brightness is a killer. If you need high throughput, then the incoherent sources are simply not bright enough. SLEDs, they have a very limited spectral range, so ultimately that boils down to limited resolution, as we'll allude on the next slide. They are very bright, they're very stable, and also the form factor and the scalability is quite attractive. However, for applications where you really need high actual resolution, the SLED is not performing. And then finally, the legacy supercontinuum lasers, these are not very stable on the spectral domain and also not so scalable. As a laser, they're very bright, and they offer an even wider spectral range than the SuperLight wideband lasers. However, for applications where you need a high sensitivity, the spectral stability will not be sufficient with your supercontinuum laser. And that's where we come in. So on both the axial resolution and the sensitivity, we'll dive a little bit deeper. So if you move to the next one, the limited bandwidth that impacts the resolution. So in OCT, The actual resolution is impacted by the spectral range of the light source. So what you see here is that both the center wavelength as well as the bandwidth of your laser, the spectral range, are impacting the actual resolution. And what we did here in this experiment is to compare ourselves with an SLED. So our both center wavelengths are identical. It's just that the SuperLight light source has 10 times the spectral bandwidth. And that's where you see how we can get to less than 3 microns of resolution. Very sharply defined edges or reflections from a movable mirror. So this is really for applications where you need to distinguish between fine layers. You need to go to a high bandwidth light source. All right, next. Then the other thing I wanted to address was the spectral stability. So legacy supercontinuum lasers, they rely on an inherently noisy process to broaden the spectrum, as you can also see in the picture. So where you talk about the complete buildup of noise, there is, and that's the formula on the right. There is, besides the detector and the shot noise of the light source, an additional component when you use supercontinuum lasers that is called excess noise. And this scales with the square of the incident power. So you can imagine these lasers are very powerful, and then also they produce a substantial amount of noise. And this noise actually limits the sensitivity of supercontinuum laser-based OCT systems. So if you look at the graphs on the bottom right, you see how ultimately you will never be able to operate in the shot noise limited range. So just once the RIN noise of the supercontinuum laser becomes dominant, you will see that the sensitivity starts to drop again. So this is a big issue for supercontinuum lasers when they're applied on OCT. Next one. So the RIN noise is a very active field of academic debate. We would like to contribute to that, of course. What's new is that, of course, we are on the chip instead of fiber, and that we alternate between positive and negative dispersion, whereas everybody else is looking at a uniform dispersion regime. So because we're chip-based, because we use PAP, we outperform on noise versus the legacy supercontinuum lasers. So the full spectrum RIN is minus 140 dBc over hertz. We also did some experiments for individual wavelengths, and these bins have roughly the size of 3 nanometers full width half maximum. And you see that we can accomplish minus 120 dB over hertz, which is about 1%. And this is really substantial improvement versus the classic supercontinuum lasers that are out there on the market. And this really helps the sensitivity of your application. Yes, then a short peek on the product roadmap. So we started with the SLP1000 battery-operated supercontinuum source. Meanwhile, we have 2 additional lasers that cover the full shortwave infrared range. One more on the bottom part, the other more on the upper part. They do tens of milliwatts of output power. What we have further planned for this year, late 26, we'll release also product for FIS near. So we target to do somewhere between 450 and 950, and also increase the power a little bit. Besides that, we also see that we can port the technology into the mid-infrared range, but that will be later in 27. Being on chip also gives us the potential to look at further vertical integration. So at the moment, we're solely focusing on the spectral broadening itself, but you can actually work in 2 directions by either onboarding the seed laser, the amplification, or more downstream towards the system. So interferometer would, for instance, be a potential candidate, or even a detector. So that's kind of what we have in mind for SuperLight. I think, Stijn, you will address more on the other OCT components as well.
Yes, thank you very much, Jeroen, for covering this exciting topic and for sharing your product roadmap with us. As Jeroen already mentioned, to help advance the OCT community, it's also relevant to bring additional building blocks, active building blocks, to the PIC platform. And this is exactly what we have been working on at LIGENTEC. So in the first part of this webinar, I talked about our general silicon nitride platform. We at LIGENTEC have also put a lot of effort into heterogeneous integration, both of thin film lithium niobate modulators, but also of III-V devices, and as well as rare earth doped amplifiers. And that is what I will be talking about in the remainder of this webinar. So if we look at the integration of III-V devices, we are leveraging our strategic partnership both with IXA but also with Exceliprint to bring heterogeneous integration of III-V actives to silicon nitride PICs at volume. And for this, we use a technique called microtransfer printing. The principle here is that we fabricate or pre-process, for example, photodetectors on the source indium phosphide wafers in this case, assuming that we make indium phosphide or indium gallium arsenide photodetectors. And we can then pick and place these pre-processed photodetectors on our host silicon nitride wafer. So we can do this in a massively parallel fashion to retain manufacturing or the capability to manufacture at scale. The advantage here is that we can still pre-test these photodetectors before we integrate them on the silicon nitride host wafer. So this is a great advantage in terms of compound yield, and essentially allows us to combine the advantage of flip chip integration, where you can also do this pre-testing, but you are limited by sequential integration, and the advantages of wafer and die to wafer bonding, where you have a volume scaling process, but you cannot do this pre-testing. So microtransfer printing combines these advantages essentially. So how does this look like? Here you can see a test chip that we manufactured in the past. So at the right of the chip, you see that we have local openings of the top oxide cladding to access the silicon nitride waveguide, which allows us to locally integrate indium gallium arsenide PDs directly on the silicon nitride. If we then test these photodetectors on our nitride chips, we see that we are achieving competitive performance. So we are reaching dark current levels typically below 10 nanoamps with a 2.5 volt reverse bias voltage, and responsivity levels near 1 amp per watt. That is in C-band, and that is the waveguide referred responsivity. So here at the bottom, you see a microscope picture where you see this local cladding opening with the photodetector integrated, and then the AN800 silicon nitride waveguide underneath the photodetector, where the light then evanescently couples from the nitride to the III-V. And then finally, we have metal RDL interconnects to connect to the photodetector and allow connecting it to a transimpedance amplifier, for example. Just to give you an example of what is possible, this is a chip that we manufactured in the past, which was a spectrometer. So this could be used, for example, for spectral domain OCT, where you have both arrayed waveguide gratings on the chip. And here we can then leverage the low insertion losses of our silicon nitride platform, but also the low phase errors and the low temperature dependence of the platform. And on the same chip, also integrate a array of photodetectors for the detection. If we then look at the source side, we also have capabilities to bring lasers and amplifiers to the PIC. And one more established methodology to do this is to build so-called butt-coupled or hybrid assembled laser diodes, which can be used for swept source OCT, for example. The idea is that you butt couple a reflective semiconductor optical amplifier to an external silicon nitride cavity, typically using a Vernier ring configuration. And this allows you to build widely tunable lasers with high output power and narrow line width. So here's another example where the chip was also packaged in a butterfly package and incorporated an additional amplifier to reach a high output power. So we have a number of published examples from several of our customers available on our website. So if you are interested in these kind of tunable lasers, I invite you to have a look at our website. Now, of course, for some applications, you may want to have several lasers or also several amplifiers on the chip for your OCT application. And this is where the microtransfer printing technology can also be of use. So we can use the same principle as what we are using for our photodetectors to integrate semiconductor optical amplifiers. In this case, instead of having PDs, we have amplifiers which we can then microtransfer print in a scalable format on the silicon nitride platform. And just to give you an example, this is a PIC that we manufactured in the context of the CSOC project. So we have a few European projects besides customer engagements where we are working on these amplifier integrations. And in this project, we were integrating both indium phosphide as well as gallium arsenide based amplifiers directly on the silicon nitride platform. In this case, we also incorporate an intermediate silicon-based coupling layer to allow low-loss evanescent coupling between the nitride cavity and the 3.5 gain waveguide. So if you are interested in this work is also published in a recent Clio Post deadline paper, which I link here on this slide. And then finally, I've been talking a lot about these 3.5 devices. We also have capabilities to bring rare earth doped amplifiers on the silicon nitride chip. And to give you an example of what is possible, this is some work that was performed in the femto chip project, where we essentially integrated a thulium doped aluminum oxide layer on top of the silicon nitride waveguide to allow pulse amplification directly on the photonic chip. So this brings me to the end. If you are interested in the technologies and products of LIGENTEC and SuperLight Photonics, I would invite you to reach out to us. We have listed here our contact information directly on the slide. And if you scan the QR code, you are also immediately directed to our website where you can find a lot more information.